In section 2.2, we look at the atomic theory of matter. In modern chemistry, we take an atomistic view of matter. That is, we describe matter as being composed of particles called atoms that are indivisible by either physical or chemical methods. This means we take a building block view of all of the objects in our universe. That is, we think of things as being made up of little building blocks, and each of those blocks is indivisible. The block just is what it is. We can assemble those blocks in all manner of different ways to create all of the objects that are around us, but any one block can't be transformed from what it is. Kind of like a Lego's building block model of the universe. Now, this idea was written down about 3,500 years ago by a guy called Democritus. There might have been people that wrote it down before him, but he was the first person that we have a record of. And he had some weird ideas about what atoms were like. He thought things like, if something tasted spicy, it tasted hot, it was because the atoms that made up that thing were on fire. And similarly, he thought if something tasted bitter, that perhaps those atoms were like spiky. So it's kind of interesting. We've moved on a long way from Democritus. In 1808, John Dalton formulated the first modern atomic theory, and we pretty much use this theory unchanged to today. He based his theory around 5 key ideas. The first idea was that all matter is composed of tiny indivisible particles called atoms. What we now know is that there are 118 types of atoms corresponding to all of the different elements that make up all of the objects in our universe. The second point that Dalton made was that atoms of one type are the same as each other, but they are different from other types of atoms. What he's really saying is every oxygen atom in the universe is identical to every other oxygen atom in the universe, but different from every carbon atom in the universe. What we now know is that this idea is not quite correct, and when we talk about isotopes in the next section, we'll be able to update this idea. The third point that Dalton made was that it is the number and arrangement of atom types in a pure substance that determine its identity. So the reason that water is because it is composed of 2 hydrogen atoms bound to 1 oxygen atom. And the reason that hydrogen peroxide is because we have 2 hydrogen atoms bound to 2 oxygen atoms. So what I hope you see is that both the number of each atom type and how they're connected to each other is what gives a pure substance its identity. The fourth point that John Dalton made was that when a chemical change occurs, what is happening is the way that atoms are connected to one another is being modified in some way. That is, that chemical change involves the combination, separation, and rearrangement of atoms. So this is a classic chemical change. It is the combustion of methane to make carbon dioxide and water. And you can see that the way that the atoms are bound to one another is radically different after the reaction than what it is before the reaction. We no longer have hydrogen bound to carbon, and we now have carbon bound to oxygen. We also have hydrogen bound to oxygen, so we've completely rearranged how the atoms are connected to one another. The fifth point that Dalton made was that in a chemical reaction, atoms cannot be created, destroyed, or transformed. However many atoms we start with, that's how many atoms that we end with. We just rearranged the way that the atoms are connected to one another. So let's talk about some basic facts about atoms. Atoms are about 10 to the minus 10 meters across, and they have a mass of about 10 to the minus 23 grams. The exact number depends on the type of atom. We can visualize atoms using a technique called scanning tunneling microscopy, where we drag a tiny tip across the surface of the sample and detect the current that flows between our sample and the tip, and from that we can extract an image of the surface. The first folks to do this were back in the 90s. They worked for IBM, and they used the scanning tunneling microscope to make the world's smallest billboard, and they were able to spell out the letters IBM in xenon atoms. Now, the reason that these scientists at IBM wanted to be able to image atoms is they were curious about the nature of silicon, which they used to make computers. So here's an older image of a silicon surface, and it's got these sort of almost hexagonal arrangement of silicon atoms, and then here's a more modern image of the silicon surface, and you can see just how sharp we're able to image those atoms. So atoms will chemically bind to other atoms to form what we call molecules, and molecules are often classified according to the number of atoms in a molecule. For example, a diatomic molecule is made of 2 atoms, or a triatomic molecule is made of 3 atoms. It's important to recognize that the atoms in a molecule cannot be separated by physical processes. That is, it doesn't matter how much we filter it, or we warm this up, or cool it down, or any of the things that we might do to separate a mixture. We can't separate the atoms in a molecule using those techniques. We might say that an atom is the limit of physical subdivision. A molecule is the limit of physical subdivision. It's the smallest unit we can get to without breaking chemical bonds. Another way of describing this is to say that molecules behave as a single discrete package of atoms. Now, quite interestingly, 7 elements are always found in nature as diatomic molecules. And there's a couple of ways of remembering what these 7 are. The first one is you go to element number 7, which is nitrogen, and you draw a letter 7. That will get you 6 of the 7 diatomic elements, and then we have to somehow remember that hydrogen is also a diatomic element. Sometimes people will remember the rhyme, have no fear of ice, cold, beer, to help them remember the 7 diatomic elements. So saying that once more, have no fear of ice, cold, beer. And that gives you the 7. So a couple of ways of us remembering what elements are always found as diatomic molecules. So we're getting to the point where we need to distinguish between what we call formula subscripts and formula coefficients. So if I have 1 hydrogen atom, I can just indicate that by writing an uppercase H. If I have 2 hydrogen atoms not chemically bound to one another, I would modify how I would indicate that by adding the coefficient 2 before the symbol for a hydrogen atom. However, if I had 1 H2 molecule where I have 2 hydrogen atoms bound together, then I indicate that I have 2 hydrogen atoms bound together using a formula subscript. Now I can put these 2 ideas together. If I have 2 H2 molecules, then I would use a coefficient to indicate that I have 2, and then a formula subscript to indicate that I have 2 diatomic molecules. So it takes a little bit of practice to get used to reading and writing these subscripts and coefficients. Okay, so we're asked to write the chemical formula for the following elements. So the first thing that we should do is list out our diatomic elements. Have no fear of ice, cold, beer. And then what I see immediately is that hydrogen is H2, nitrogen is N2, and then because neon is not one of my diatomic 7, I know that it's what we call a monatomic element. It's just going to be a straight up neon atom. Now, we're getting these symbols from the periodic table and also the list of element names and symbols. So hydrogen is one of the 7 diatomic elements, so we're going to write its formula as H2. Nitrogen is also one of the 7 diatomic elements, so we write its formula as N2. And neon is what we call a monatomic element, so we just give the atomic symbol for neon. It's important that you learn the 7 diatomic elements, or you're going to be confused when it comes to answering story problems. In addition to classifying molecules according to the number of atoms contained within the molecule, we might also classify a molecule according to the types of atoms that are present in the molecule. Homoatomic molecules contain atoms of the same type. A pure substance containing homoatomic molecules is an element, so our 7 diatomic elements are composed of homoatomic molecules. Heteroatomic molecules contain atoms of different types, and this means that a pure substance containing heteroatomic molecules must be a compound. So water, H2O, is composed of heteroatomic, triatomic molecules. Now, it's important to recognize that not every compound is composed of molecules. Some compounds are composed of electrically charged particles. These are called ions. And so it's important to realize that no ions exist in compounds that are made of, no molecules exist in compounds made of ions. Instead, what we have is a crystal where we have a regular repeating pattern of the positive and negatively charged ions. What we tend to do for an ionic compound is we will write the formula unit. The formula unit represents not the ions that are present in one molecule, but rather the smallest whole number ratio of ions that results in no electrical charge. So in the case of sodium chloride or table salt, if we have one of the +1 sodium ions combining with one of the -1 chloride ions, we would get 0 electrical charge. So for that reason, we write the formula unit of sodium chloride as NaCl. So, if we identify that we have a pure substance, there are 2 possibilities for what it might be. It could be an element if there is only one kind of atom present. Now, the elements can be divided into 2 further categories. Most of the elements exist as individual atoms. These are sometimes referred to as monatomic elements. And some of the elements exist as homoatomic molecules, and these include our 7 diatomic elements. If our pure substance is composed of 2 or more kinds of atoms, then it's what we call a compound. And compounds can be divided into 2 categories. There are those compounds that are composed of heteroatomic molecules, and they have molecules as their structural unit, where we have a group of atoms chemically bound together acting as a discrete unit. Or they might be composed of positive and negative ions, in which case they will be crystalline and there will be an approximately infinite repeating pattern of these positive and negative ions building up what we call a crystal. Okay, so that brings section 2.3 to an end.